Hey everybody, it's Ripley again. We're in section 3.7, derivatives of logs. It's really the last set of functions, like real common functions that we learned in Algebra 2 and pre-calc that we need to be able to take a derivative of, okay? So there's a couple of things to remember here. First things first, let's just discuss logarithms. If I talk about the natural log of x, we know that this is log base e of x. I also know that if I'm talking about the log of x, this is log base 10 of x. This is called the natural log. This is called the common log. I know one other thing that's really important to remember is that log base a of x, if I want to change its base, we did this before, I can do this as log base b of x divided by log base b of a, which is just the change of base. This could also be written as the natural log of x over the natural log of a, the common log of x over the common log of a. Okay, so just standard issue. We've seen this before. So what I really want to know is what is the derivative of, let's start easy. Let's do the natural log of x. That's what I want to know. So, you ready? Let's head this away. I'm going to say y equals the natural log of x. Now again, if I don't have to, if I have other more powerful tools, if I don't have to, I don't want to start this whole thing with the limit as h goes, that's an m by the way, as h goes to 0 of et cetera, et cetera, et cetera. That's kind of a pain in the butt, right? So I'm going to cheat. Watch what I do here. I'm going to use algebra. I know that this is going to turn into e to the y equals x, right? And then I'm going to use implicit differentiation. These are algebraically equivalent. There is no difference. So I'm going to take the derivative with respect to x of e to the y equals x. Well, the derivative of e to the blah is e to the blah times d blah, right? Which in this case, the derivative of the blah is, this is the blah, right? That's my y. Derivative of y is 1 times my footnote, because I just differentiated y as though it was an x. All right? Now, that's magic, because that is the thing I'm looking for, right? The derivative of y is dy over dx. And then, of course, this equals 1, right? So in a real quick blast of algebra, if I solve for dy over dx, which is what I wanted, right? Isn't it just 1 over e to the y? Look close. E to the y was x. So the derivative of the natural log of x is just 1 over x. That's all that it is. Now watch this. How about the derivative of any other logarithm? If I take log base a of x, all right? If any other logarithm. Well, okay, so I'm going to take y equals log base a of x, and I'm going to play. But before I play, I'm going to change the bases. Look, the derivative of the natural log of x was a piece of cake. It's just 1 over x, right? So why don't I change the base and turn this into the natural log of x over the natural log of a? And then all I have to worry about is the fact that this thingy-dingy right here is nothing but a constant. It's just a number. It's a goofy-looking number, but it's a number nonetheless, right? So really I could think of this as 1 over the natural log of a, just a constant, times the natural log of x. Now notice I have done no calculus. I've just done algebra. Well, this implies that the derivative, if I take the derivative of this guy, so d over dx, is of 1 over ln a times ln x, is just the constant, which is along for the ride, right? It's just right there. I'm not going to use product rule. That would be silly. Times, hey, look at that, 1 over x. Isn't that awesome? So the derivative of log base a of x is 1 over ln a times 1 over x, which if we want to clean it up algebraically, this is just 1 over x. All right. Now you got to be careful, folks. I can't say this vehemently enough. All other rules apply. So if I take the derivative of, I don't mean to condescend here, but I'm going to have to beat on you guys. If I compose f into ln, hopefully a little bell or a little flag goes up in my brain that says, ooh, 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 composition of functions. So this is really just the natural log of blah. The derivative of the natural log of blah is 1 over the blah, which in this case is f of x, times the derivative of x, which is f prime of x. So let's say, for example, if I'm looking at the natural log of sine of x. Now, really, that doesn't really work. Let's do something where I don't have to worry about it being negative, right? Because I can't remember the domain of logarithms is positive reals. So let's see, let's do x to the fourth plus x squared plus 1, right? Well, then the derivative is, this is just the blah. The derivative of the natural log of blah is 1 over blah, x to the fourth plus x squared plus 1 times the derivative of the blah, which is just 4x cubed plus 2x. I clean it up, and I get 4x cubed plus 2x over x to the fourth plus x squared plus 1. Nothing to it. Okay? Similarly, what if I take the limit? Wow, talk about a flashback. What if I take the derivative of something like f of x equals the natural log of, let's go x plus 1 over x minus 1, and let's make x greater than 5, just so we don't have to worry about this thing ever being negative. All right, well, it's the same thing. F primed of x. This guy right here is just my blah. It's the thing that's being composed into natural log of x. Okay, so this ends up being 1 over x plus 1 over x minus 1, which we know is just the reciprocal. And then I have to use quotient rule, low d high, x minus 1 times 1 minus high d low, x plus 1 times 1, all over low squared, x minus 1 squared, right? So clean it up. 1 over any fraction is the reciprocal of that fraction, so I get x minus 1, x plus 1, times, let's see, x minus x is 0, negative 1 minus 1, that's negative 2. I think we've actually done this one before, haven't we? This is x minus 1 squared. One algebraic step plus my derivative. However, excuse me, I'm going to sneeze. Gesundheit to me. X minus 1 goes away here, and one of these guys goes away. Simple algebra. And this ends up being negative 2 over x plus 1 times x minus 1. And I'm done. So all of your old derivative rules, every new thing that we do, your old derivative rules still apply. Hey, I wanted to throw one other thing in here just because it's fun to talk about. We've talked about it before. You've seen it. It's the definition of E. Let's make sure we all understand where E comes from, because that's going to be pretty useful for down the road, and this seems like a pretty good time to talk about it. Okay? The first thing is, let's see, what do we know? We know that E can be defined as the limit as what? X goes to infinity of 1 plus 1 over x to the x. And you could actually do this with your calculator if you wanted to. You could plug in, you could let x get bigger and bigger, plug this guy into your calculator, let x get bigger and bigger, and see what it heads for. All right, another way is that we define it is the limit as x goes to 0 of 1 plus x to the 1 over x. And if you think about it, these are really virtually the same thing. If I just let notice as x goes to infinity, this goes to 0 and this goes to infinity. As x goes to 0, this goes to 0 and this goes to infinity. So they're really the same thing. Okay? So, guess what, ladies and gentlemen? You are ready to rock and roll. You have everything that you need to understand derivatives, pretty much. We'll play a little bit more with some fancy derivatives down the road, but for right now, you're pretty much where you need to be. Thanks for listening. Have a great day. I'll see you tomorrow.